As we discussed in Lesson 7, there can be lots of carbocation rearrangements that occur when you use an alkylation reaction with benzene. Therefore, most commonly what we use instead is an acylation reduction to link most chains to benzene. And what that means is that the first thing that you would use is an acyl chloride or anhydride, so that you have a C-double-O bond here, because that does not allow a carbocation to form right there, nor rearrangement to occur. So once you have that positive charge here as the electrophile, it will react, and that's the carbon that will attach to the benzene. You can then go through several different forms of reduction in order to yield your desired substituent off of that benzene ring, each of which has their own advantages. H2 and PDC is very simple to do. This also will reduce NO2 and several other things too, so you have to be very careful about using that because it can reduce several different groups. We then have both acid conditions and basic conditions that can also go through this reduction. This is called the Clementine reduction with zinc and mercury, HCl, and heat. You can also go through the Wolff-Kishner reduction with this hydrazine OH minus and heat. The advantage of this guy, in addition to being in basic conditions, is that it does not reduce NO2. Part of the reason why we look at doing different types of conditions in order for these reductions to take place is simply because we like to have variety. If you have something that will react with HCl further down this R group and you don't want it to, then you probably need to use a base condition, or maybe even this condition. That way we can selectively pick which reaction we want, which products we want, and selectively determine which of those functional groups will actually react. So there's two other ways that's commonly used of getting a benzene to react with an alkyl group. The first being organocuprates. Notice here we do have to start with an alkyl halide to give the R group there, and that will not rearrange. Nor will using the Suzuki reaction. So this is an organoborane. Whatever was originally attached to the boron, that carbon is what's going to replace the alkyl halide. Same thing here, whatever's actually attached to the copper here is where that replacement will take place. Some other helpful reactions when it comes to synthesis. Whenever you have an alkyl halide, period, if you react that with an H2, you could end up having a replacement reaction, and therefore you get an H2. Now this reaction you have to be careful with. We'll talk about that one later. You want to add a little bit of a base there, basically to rid out your HBr. Ronnie nickel will take a cyano group and basically turn that into CN. This one's hard to see sometimes when you're doing retrosynthesis, so that's a good highlight, if you will. This is palladium on carbon. Note again that that will take out the NO2 to NH2, just as it will a C-double-O bond. So if you want both those things to happen at once, great. Just let that happen at once. You cannot selectively choose whether or not the NO2 or the C-double-O bond will work. Actually, both of them will at the same time. This is a really interesting reaction. If you have any benzylic hydrogens, so here we've got 3, here we've got 1, this is a tertiary alkyl halide. We don't have any. But it just needs, the H2CrO4 just needs 1 benzylic hydrogen. And if it grabs a hold of that, it will turn the entire thing to COOH. So whatever's out here, it doesn't matter. It's gone. You replace it with COOH. So COOH, COOH. This one it doesn't touch because you don't have that benzylic hydrogen. Here's the reaction conditions it takes to break up the aromaticity of benzene and give you cyclohexane. Okay, 25 atmospheres of pressure. That is a massive amount of pressure that basically we can barely even fathom. 250 degrees Celsius, that's very high. And a catalyst, oh yeah, you need some hydrogen there too. That's what it takes to interrupt that aromaticity. When we say that that is really, really, really stable, not kidding, it's really, really, really stable. Naming. Okay. So this is a little bit of a different topic from what we were talking about before. But when we're talking about polysubstituted benzene, what we first want to do is use those names we were talking about earlier. So here we would say that that would be aniline, for example. And whatever other substituents you have over there, you could sort of name them just as we always had before, as in 1, 2, 3, 4. Or you could say that this would be like 3, whatever it is, aniline, okay? Another way to name that we typically use, it's kind of old, it's just left around from where we've done it for so long. This position that's next to the primary group that we're naming our benzene from will be called the ortho position. I don't know why, but this makes sense to me because it's orthogonal to what you're looking at. This one's the meta position. So see how this is like the middle between that and that? That's where your meta comes from. And this is the para position. And we use these terms typically in disubstituted benzenes because it doesn't make sense past that really. So this would become meta-ethyl-aniline or 3-ethyl-aniline. They're the same thing and we would use those interchangeably. But I want you to know where that meta-ortho-para come from because we're going to use it extensively in the next section here. If you have more than 2 substituents, you would use the lowest total number as we've seen before. So if this is our aniline, we would go 1, 2, 3, 4, not 1, 2, 3, 4, 5, right? So this becomes 4-bromo, 3-ethyl-aniline. And no, once you get to a tri-substituted benzene, usually we keep that separate from the orthometa, usually. This would be 4-bromo, 2-chlorophenol, because phenol is our major substituent here. And down here we have 3-bromo, 2-chloro-nitrobenzene. Thank you very much. I hope you have a good day.